Welcome to Tomorrow Unveiled. Today, we're embarking on a really fascinating deep dive into green code, hot core this week in energy breakthroughs. You really have to imagine this truly seismic shift happening right now in the global energy landscape. It's like a strategic reevaluation it's fundamentally rewriting the green code. It's focusing on technologies our research team is calling hot core. It's a story where things like density, reliability, and security are rapidly becoming the new cornerstones of clean energy. Our mission here on Tomorrow Unveiled is to unpack these big policy shifts, the groundbreaking investment trends, and of course the exciting tech advancements reshaping our energy future. And crucially, explain why this pivot seems to be happening right now. Just to be clear, all the information and insights we're sharing, they come from extensive research compiled by our dedicated research team, drawing from multiple credible sources across the energy sector. And understanding these changes, well, it isn't just for industry insiders. It's vital for everyone, really. I mean, these shifts directly impact our grids, our economy, even the air we breathe. So let's unpack this.
It truly is a fascinating moment.
Yeah.
What we've observed this week, especially with this U.S. One Big Beautiful Bill Act, the ODBBA, signed on July 4th, 2025.
Yeah.
It's not just tweaking things. Our research team's analysis indicates it's a deliberate, almost radical attempt to re-engineer the nation's entire energy future.
A strategic shockwave, you might call it.
A strategic shockwave. That sounds about right. So what exactly are the key changes this legislation introduces, and what does it do to those existing incentives we heard so much about?
Okay, so the OBBBA dramatically tightens the screws on the production tax credit, the PTC, and the investment tax credit, the ITC, specifically for wind and solar projects. To qualify now, these projects have to begin construction by July 4, 2026, or be placed in service by the end of 2027. That's a severe acceleration. It's basically, like you said, pulling the rug out from under many planned projects.
Oh, okay. But in stark contrast, the Act largely preserves and even enhances favorable tax credits for things like advanced nuclear, geothermal, and battery storage. It even adds a new 10% bonus credit for advanced nuclear facilities if they're located in designated energy communities. Places historically reliant on fossil fuels.
Right, those energy communities. So if this is a strategic shockwave, what's the core reason? Why such a dramatic pivot towards these hot core technologies now? What's the strategic thinking here?
Well, but the rationale seems to be twofold. Directly addressing two major pressures we're seeing. First, there's just this explosive electricity demand. We're seeing it from new loads like massive AI data centers and, the widespread adoption of electric vehicles. These aren't just adding a bit to demand. They require truly 247 ultra-reliable power, that baseline power.
Okay, the demand side. And the second?
The second is tackling a critical geopolitical imperative, breaking dependency on, frankly, foreign supply chains. By rewarding technologies with greater potential for domestic manufacturing, the U.S. is aiming for significantly greater energy independence and security. This policy is a clear bet on density, reliability, and security over, say, intermittency and extensive land use.
That paints a very clear picture of the intention, yeah. But a shift this aggressive, it must have immediate consequences, right? What's the economic fallout we're actually seeing on the ground from this policy?
Right. Our research team provides an impartial overview here. So far in 2025, the numbers show over $14 billion in clean energy investments, and about 10,000 associated jobs have been canceled or downsized. Furthermore, the analysis indicates over 100 gigawatts of U.S. solar and wind projects are just no longer economically viable under these new rules. And in the battery sector specifically, 21 gigawatt hours of planned battery energy storage battery projects canceled just due to the sudden business uncertainty.
That's a significant disruption, no doubt.
It is. It's a major shakeup.
Okay, so that's a considerable upheaval domestically, but is this purely a U.S. thing? Are we seeing similar trends globally that kind of validate this hot core pivot?
That's what's really illuminating, actually. The global picture seems to validate this strategic shift. The International Energy Agency released its 2025 Global Energy Investment Report just this week, July 24th. It shows global energy investment hitting a record $3.3 trillion. Okay, with an unprecedented $2.2 trillion flowing specifically into clean energy.
Wow, $2.2 trillion in clean energy.
Exactly. And here's where it gets really interesting for our discussion. The IEA report explicitly calls out growth in batteries and nuclear energy. It projects battery storage investment alone to reach $66 billion in 2025. And it directly links this surge to AI plus energy, the data center effect.
Ah, so it's not just a feeling. The data shows that AI connection.
Precisely. It's clear the world is recognizing the same demands for reliable, dense power that seem to be driving the OBBA.
Okay, so we're seeing policy and global investment starting to align. Now, how does the broader geopolitical picture fit in here? What's the strategic play beyond just domestic policy?
Well, the U.S. State Department's recent announcement, a new foreign assistance package for the Philippines, gives us a direct example. This package specifically targets energy and semiconductor development in the Luzon Economic Corridor. There's a $15 million carve-out from over $60 million total, plus over $21 billion in pledges from U.S. companies. Our research team sees this as a proactive strategy, basically building secure, allied supply chains that can compete with the existing China-centric ones.
Right, diversifying away.
Exactly. It's a complementary move to the Domestic Foreign Entity of Concern rules, the FEOC rules, which aim to exclude components and materials from, adversarial nations. It's really about building a parallel industrial ecosystem for these critical technologies.
It definitely sounds like we're not just talking about policy and investment shifts, but a really high-stakes global repositioning. Okay, let's get into the exciting stuff. The technological advancements themselves, the ones at the heart of this hot core strategy. What's the absolute latest in nuclear fusion?
For decades, it felt like it was always,
Yeah.
30 years away.
Yeah, that old joke. But the progress now is actually remarkable. Global private investment in fusion jumped by $2.64 billion in just the last year. That's a staggering 178% increase. Total funding is now nearing $10 billion across 53 companies worldwide. That signals, I think, a growing confidence in commercial fusion deployment actually happening.
$10 billion, that's serious money moving in.
It is. And we're also seeing significant scientific gains. Germany's Wendelstein 7X Stellarator, that's a complex sort of donut-shaped device using magnetic fields to contain superheated plasma.
Right, the magnetic confinement. Exactly. And the UK's GT Tokamak, a similar but slightly different approach, have both set impressive new heat output records. And then you have companies like Commonwealth Fusion Systems, CFS. They're actively building their Spark tokamak right now, manufacturing the high-temperature superconducting magnets. They've even secured a landmark 200-megawatt power purchase agreement with Google for power delivery in the early 2030s.
Google buying fusion power for the 2030s. That's a statement.
It really is. And adding to this momentum, the U.S. Nuclear Regulatory Commission decided to classify fusion power plants under a more relaxed framework, kind of like particle accelerators. That should simplify future licensing and really encourage these private ventures.
So does this all mean deployment timelines are actually shrinking? Are we truly looking at the early 2030s for grid connection? That feels incredibly fast.
Well, an industry survey our team looked at shows that 84% of respondents expect fusion-generated electricity delivery by 2030, and 53% are targeting 2035 specifically. So yes, this indicates very strong and growing confidence in commercial viability within the next decade or so. It's moving firmly out of the realm of, pure science fiction.
It's just astounding. Mind-blowing, really. But okay, while fusion is still scaling up, advanced nuclear fission and especially small modular reactors, SMRs, they seem to be making major strides right now as these flexible powerhouses. What are we seeing there?
Yeah, SMRs are really buzzing. A new report from our research team shows an explosion of interest and progress. There are now 127 different SMR designs under development worldwide. That's up from 98 not long ago. There's been an 81% jump in funded concepts, and get this, 51 designs are already in various licensing processes globally.
51 in licensing, so these aren't just drawings anymore.
Exactly. These aren't just concepts. We're seeing concrete examples like Kairos Power completing the actual reactor vessel for its Engineering Test Unit 3. NuScale Power has consolidated regulatory approval for its 77-megawatt electric design, which can scale up to 924 megawatts by just combining modules. And Doosan in South Korea is already manufacturing 12 of those modules for rapid deployment. TerraPower's Natrium reactor also advanced through multiple regulatory milestones just this week.
And what's really interesting is the international cooperation you touched on earlier. Are other countries actively joining forces here, seeing similar benefits to this hot core idea?
Absolutely. It's a global trend. Poland's Orlen Synthos Green Energy is partnering with Canada's Ontario Power Generation for GE Hitachi's BWRX 300 SMRs, aiming for 2030. The UK and the Czech Republic just announced a strategic partnership for up to 3 gigawatts of SMR capacity by the mid-2030s. India is developing 3 indigenous SMR types, including one specifically for hydrogen production. Even Sri Lanka is laying the groundwork for its first nuclear plant, supported by an IAEA mission. It's a truly global effort driven by that need for reliable, dense power.
Okay, but a significant hurdle for fission, the one people always bring up, is nuclear waste. What progress is being made there? Is anything changing?
That's a crucial point, yeah. And we are seeing breakthroughs. Moltex Energy, for example, announced a significant step forward with its waste-to-stable salt process. They call it WATS. They successfully extracted over 95% of the long-lived actinides. Those are the highly radioactive elements that are the main concern in spent fuel from used CANDU reactor fuel. That's a common reactor type.
Over 95%. That's huge.
It's huge.
Yeah.
This dramatically reduces the volume and longevity of the hazardous waste. And importantly, the process potentially creates new fuel from what was waste. It's potentially a real game changer for the long-term sustainability picture of nuclear power.
A game changer indeed. Okay, speaking of sustainability and enabling these systems, let's shift focus slightly to high-density energy storage. This feels like a crucial part of the whole green code for making grids reliable, doesn't it? I mean, even hot core needs effective storage.
Oh, absolutely essential. You need storage to optimize any grid,
Ah,
especially one with diverse sources. And we're seeing big moves here too. Volkswagen's battery subsidiary, PowerCo, and the U.S. startup QuantumScape have expanded their collaboration. They're working to industrialize QuantumScape's lithium metal solid-state battery cells.
solid state, that's the next big thing, right?
That's the hope. It's a major leap because solid state promises higher energy density. So more power in a smaller, lighter package. Faster charging, they're talking 5 to 10 minutes. And improved safety over traditional lithium-ion. This partnership aims to eventually mass produce up to 80 gigawatt hours per year, enough for about 1 million EVs annually.
Wow. And beyond EVs, grid applications.
Definitely. Our research team indicates that investment in battery storage for the power sector alone is projected to hit that $66 billion mark in 2025 we mentioned earlier. You see companies like General Motors supplying redwood materials with both new and second-life EV batteries for stationary grid storage. And the impact is real. The significant build-out of batteries in California, for example, has already led to a 12% year-over-year reduction in solar curtailment.
Meaning less wasted solar power.
Exactly. Less wasted solar power when it's generated, but maybe not immediately needed. Batteries soak it up for later.
Okay, this is all incredibly fascinating. Before we dive deeper into the sustainability impacts and the future outlook of these shifts, just a quick word for you, our listeners. If you're finding this insightful on YouTube, please take a moment to like this video, subscribe to Tomorrow Unveiled, and maybe hit that notification bell so you never miss an update on the future. And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners, and we genuinely love hearing your thoughts. So whether you're on YouTube or your favorite podcast app, leave a comment. Let us know what you think about this week's energy breakthroughs. All right, let's talk more about the sustainability side of this pivot, especially land use. Nuclear and these other hot core technologies are often praised for their density, their small footprint. But how much of a difference does that really make on the ground?
It makes a monumental difference, honestly.
Mm-hmm.
Our research team pulled together some compelling quantitative comparisons. Nuclear power has an incredibly minimal land footprint. We're talking 18 to 27 times less land than solar PV, and a staggering 50 times less land than coal for the same energy output.
50 times less than coal.
50 times. To put that in perspective, a single standard 1,000 megawatt nuclear plant typically occupies just 1 to 1.5 square miles. A solar farm trying to produce that same reliable output, it would sprawl across dozens and dozens of square miles.
That's a stark contrast. What about emissions, life cycle emissions?
Also incredibly low. Advanced nuclear reactors have estimated life cycle greenhouse gas emissions around 9 to 12 grams of CO2 equivalent per kilowatt hour. That's comparable to wind energy, actually significantly better than utility-scale solar, and of course orders of magnitude better than any fossil fuel.
Okay, that raises another important question, though. What about resource usage? Things like concrete and steel. We hear about that a lot with large infrastructure projects.
That's a fair point. But nuclear plants, for instance, actually use the least concrete and steel per unit of energy generated compared to many other sources. And going back to density, uranium fuel itself has that unrivaled energy density, remember, 1 million times more energy per kilogram than coal. This inherent density means a very, very small waste stream volumetrically. In fact, all the U.S. spent nuclear fuel ever produced in the entire history of nuclear power could theoretically fit onto a single football field. stacked just a few meters deep.
A football field. That really puts the volume in perspective.
It does. It's a remarkable testament to how much energy you can get from so little material.
Okay, that addresses the volume. But what about those long-standing concerns about nuclear waste safety and overall plant safety? Beyond just the volume, it's about the perceived risk people worry about.
That's a very valid concern, and it's one that modern advanced reactor and SMR designs are directly engineered to address. Many incorporate passive safety features, things like gravity-driven cooling systems that don't need active operator intervention or external power to work in an emergency. They fail safe, essentially.
Okay, passive safety.
Right. These smaller reactors can also potentially be sited underground, which enhances security against external threats. And as we discussed with Moltex's Watts process, breakthroughs in recycling are a potential game changer for the waste issue, dramatically reducing volume and longevity, making long-term geological storage far more manageable, is still needed. And of course, fusion, if realized commercially, promises no meltdown risks and no long-term radioactive waste at all. That offers an even cleaner potential future.
So it feels like the technology is advancing to address these historical concerns. But let's circle back to the OBBA's strategic pivot here in the U.S. On the one hand, these advancements. On the other, you mentioned some immediate negative social and economic fallout. Can you give us that impartial overview of that flip side again? What were the direct consequences?
Sure. Our research team impartially reports those direct consequences. The accelerated tax credit phase-out, as we noted, has directly led to the cancellation of over $14 billion in planned clean energy investments, and the loss of around 10,000 jobs just in 2025. Estimates also suggest over 100 gigawatts of U.S. solar and wind projects are basically no longer economically viable under these new rules. There are also predictions, we should mention, of potentially higher household energy bills in some areas due to removing incentives for what were, until recently, the cheapest forms of new generation to build.
Right, the levelized cost argument.
Exactly. And it's also worth noting, just for context, that a significant portion of these canceled investments and jobs were actually located in Republican-led states, which highlights the complex political dimensions of such a dramatic policy shift. It's not a simple picture.
No, definitely not simple. So, given these pretty strong policy headwinds now for low-density sources like wind and solar in the U.S., does this mean it's sort of the end for them in this new energy paradigm? Or do they still have a crucial role?
Not at all the end. While they face significant policy headwinds, especially at the utility scale driven by regulation, corporate demand for wind and solar remains remarkably robust. For example, Meta just signed a power purchase agreement for a huge 600-megawatt solar project in Texas. Canadian pipeline giant Enbridge made a $900 million investment in Texas solar, also backed by Meta. Microsoft just activated its 408-megawatt Ash Creek solar project this week.
So corporations are still buying big.
They are. What seems to be emerging, based on our team's analysis, is a kind of bifurcated market, two tracks. Utility-scale development for regulated markets. That will likely pivot hard towards firm, reliable power, driven by policies like the ODBBA. But corporate procurement, especially in deregulated markets like Texas, will continue driving new renewable energy builds because the economics for them can still work and they have their own climate goals.
Okay, so two different markets developing. What about the relationship between these hot core and low-density sources on the grid?
That relationship seems to be shifting from purely competitive, maybe, to increasingly symbiotic, complementary. The hot core technologies like nuclear provide the firm 247 baseload power and the reliability services, the grid stability. That, in turn, enables the grid to safely and affordably absorb vast amounts of cheap but intermittent renewable energy from corporate PPAs and other sources. We saw a glimpse of this in the Texas grid recently, actually. During an unexpected coal plant shutdown, solar and wind managed to provide up to 50% of the power for a time.
Wow, 50%.
Yeah, which highlights the immense potential of renewables. But it also implicitly underscores the critical need for that firm baseload support, especially during periods of intermittency or unexpected fossil fuel outages, particularly when demand surges. One enables the other, really.
That makes a lot of sense. A kind of complementary dance rather than an outright competition. So looking ahead then, let's talk timelines again. When can we realistically expect these hot core technologies to actually come online and truly start impacting our grids in a big way? What's the outlook?
Okay, timelines. Based on our research team's synthesis of announcements and projections, they are indeed accelerating, but obviously with varying degrees of certainty. For SMRs, small modular reactors, the first grid-connected units are realistically expected by the end of this decade or into the early 2030s. For instance, Ontario Power Generation's Darlington BWR X300 in Canada is targeting 2030. Rolls-Royce and EEZ in Europe are aiming for the Czech Republic's first SMR by the mid-2030s. NuScale's VOIGR plant is slated for 2029, so late 2020s, early 2030s seems plausible for first-of-a-kind SMRs.
Okay, SMRs within the next 5–10 years. What about advanced fission and that waste recycling?
For those, demonstration projects of novel reactors like Moltex's waste-burning SSRW and TerraPower's Natrium reactor are expected in the early to mid-2030s, so slightly further out for those more advanced concepts. Fusion, as we discussed, most companies are targeting the 2030s for the first grid-connected pilot plants. CFS aiming for early 2030s, Helion targeting 2028, just for an electricity demonstration. So commercial fusion power is likely still more mid-2030s or later, realistically.
And the solid-state batteries, when might we see those in our EVs or on the grid?
The Volkswagen QuantumScape partnership suggests maybe a 3 to 5 year horizon to reach automotive-grade mass production. That means commercial EVs with solid-state batteries could possibly appear around 2027-2028. Grid applications might follow shortly after as production scales up.
Okay, those are still incredibly ambitious timelines across the board for such transformative technologies. What's the biggest hurdle? The biggest impediment to this rapid transition actually happening on schedule? There must be a critical challenge.
There is. And the consensus from our research team, looking across all these technologies, points to one thing: the supply chain. The aggressive EFOQ rules aimed at excluding Chinese and Russian involvement, combined with this rapid pivot towards nuclear and advanced batteries, creates immediate and frankly massive demand for non-Chinese nuclear components, processed critical minerals, battery materials, you name it. The Western industrial base is simply not currently equipped to meet this sudden surge in demand. It's just not there yet. For context, our team found that over 92% of nuclear reactors that started construction worldwide since 2017 used Russian or Chinese designs and their associated supply chains. 92%.
Wow. Okay, so that creates a huge gap.
Exactly. It creates what we're calling a supply chain paradox. The policy demands a rapid shift to a secure allied supply chain that, well, it doesn't really exist yet at the required scale. Building this parallel industrial ecosystem, reshoring manufacturing, developing new mines and processing facilities, training workers, it's a multi-decade, multi-trillion-dollar endeavor. That represents the critical vulnerability. It's the primary source of potential project delays and significant cost overruns for all these ambitious plans. It's a truly monumental challenge.
It really sounds like a high-stakes wager then. A massive bet on our collective ability to not just innovate the tech, but to completely retool global industry at an unprecedented pace.
It absolutely is. You've hit the nail on the head. This whole pivot is indeed a high-stakes wager. It's betting that the long-term benefits, energy security, reliability, decarbonization via high-density sources, are worth the significant short-term economic disruption we're seeing and worth tackling the immense challenge of building an entirely new industrial ecosystem almost from scratch in some areas. Success, ironically, might depend less on the final elegance of the fusion reactor or the SMR design and more on nuts and bolts industrial policy and solving this monumental supply chain paradox.
A true test of industrial will, as you said.
Exactly.
We have covered so much ground in this deep dive into green code, hot core, just incredible stuff happening. As we wrap up, what are the key takeaways for our listeners, the essential nuggets to carry forward from all this?
Okay, key takeaways. I think number one is that the global energy system appears to be making a decisive strategic pivot towards these high-density, hot-core technologies, advanced nuclear, fusion, high-density storage. Number two, this shift seems driven primarily by soaring electricity demand, particularly from new sources like AI, and renewed geopolitical rivalry, pushing for energy independence and secure supply chains. Policies like the ODBBA are accelerating this, and global investment trends are validating it. Number three, these technologies offer significant advantages: minimal land use, very low life cycle carbon emissions, and the promise of stable, continuous power. And finally, while lower density renewables like wind and solar face new policy challenges in some markets, they continue to grow, especially via corporate demand, and seem to be shifting into a more complementary, symbiotic role within this evolving energy mix.
A comprehensive summary. Okay, so as we look to tomorrow, what's one final provocative thought for you, our listener, to carry forward from this week's breakthroughs? Something to mull over.
I think it's this. The embrace of hot core technologies genuinely offers a potential future where energy isn't just clean, but truly abundant and deeply secure. However, achieving that future challenges us profoundly. It requires us to rapidly build not just cutting-edge technology, but entirely new global supply chains. And critically, it requires fostering widespread public understanding and acceptance for what is truly a monumental multi-decade transition. It's really a test of our collective industrial will, our policy-making skill, and our shared vision for the energy system of the decades to come.
A test of our collective will and vision. A perfect thought to end on. And that is our deep dive for this week on Tomorrow Unveiled. Once again, if you found this insightful on YouTube, please do take a moment to like the video, subscribe to Tomorrow Unveiled, and turn on those notifications. You won't want to miss what's next. And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us that rating and review for Tomorrow Unveiled. It really does help new listeners discover the show. We always love hearing your thoughts too. So whether you're on YouTube or your favorite podcast app, please leave a comment. Let us know what you think about this week's energy breakthroughs and this whole hot core shift. Join us next time for another deep dive into what tomorrow unveils.